Hello everyone, this is Dr. Young, and in this video we are going to start talking about how to identify different types of reactions. We're going to start with precipitation. In order to talk about precipitation, we're also going to talk about some of these solubility rules, just some general rules of thumb to help you identify if you just look at an ionic compound, is it likely to be soluble or insoluble in water? So, types of reactions, just in general here, this is just kind of a helpful way to sort information and to sort of categorize things that might be important for you. So, and there's many ways to do it. I've given you 3 totally different ways that people might categorize things. The first is just single replacement, double replacement, decomposition, etc. That's all about what's going on with just your formula. Like if you know no chemistry, what's going on with your formula? Are you replacing 2 things? Do you have one thing that's decomposing into 2 things? Do you have 2 things that are synthesizing or combining to form one thing? So that's one way to look at equations. We're not going to spend a lot of time on that because we're chemists, and so we want to talk about the actual chemical reactions going on. Second, I have here addition, elimination, redox, and substitution. That might be something that you're going to see when you take organic chemistry. So in the future, we care a lot about SN1, SN2 reactions, dehydration reactions, electrophilic aromatic substitution reactions, all these different classes of reactivity. What I want to focus in this video and the next few videos are these categories of precipitation, acid-base reactions, combustion reactions, and redox reactions, right? We're going to have 4 different videos on each of these types of reactions. And the goal is to get you to a point where you can look at these reactions and be like, oh, this is combustion. This next one right here, this is a precipitation reaction. The next one is a redox reaction. And then this last one here is an acid-base reaction. And so how on earth do I know that? I mean, once you get trained into this, you should be able to just kind of glance at these and be like, oh yeah, this, that, and this, that. So what we're going to do in this video is focus on what's a precipitation reaction, how do you identify it, and what are the solubility rules that we need to know in order to help us identify a precipitation reaction. So precipitation reaction, here I have lead nitrate combining with potassium iodide to make potassium nitrate and lead iodide. This is a very classic precipitation reaction. It's in like every general chemistry book, and these pictures are online everywhere. And the idea is that you're taking this clear colorless solution, you pour it into another clear colorless solution, and this yellow solid starts to form, is the idea. This yellow solid starts to form. And so you have these 2 solutions here, right? So both of the reactants, both of the reactants here, they both have an AQ after them, right? Which means they're soluble in water. The AQ means aqueous, soluble in water, right? So that's one key feature you're going to see is that they're both water soluble, which is why our solutions here, right, are clear. In this case, they're clear and they're colorless, but they're clear. You can see through them, right? They look just like water. You can't even tell that lead nitrate or potassium iodide is in them just by looking at them. And the other thing that you're going to see in these is that one of the products is going to be a solid, or in other words, it's not soluble in water. And in this case, that's this yellow stuff, right? We can very, very clearly see this yellow solid. And if I look up at my reaction, apparently that yellow solid is the lead iodide, right? This is the yellow stuff. So when I mix these 2 reagents, the lead nitrate and the potassium iodide, it forms this yellow solid, this lead iodide. We've kind of rearranged these atoms to make new compounds here. And then I'll lastly say that another way to help identify it, in addition to that you start with 2 water-soluble reactants and you always end up with a solid product, is that it's a type of double replacement reaction. And I don't know that we've talked about these too much, but the idea with the double replacement reaction is that you take something like just generically an AB, some ionic compound that's A and B, with something that's X and Y, some XY thing. And a double replacement means you switch the things that are cations. So in this case, A would be my cation because it's first, and X is my cation because it's first, and you just switch their places here. You just swap them. It's a double replacement. You're doubly replacing these things, which means I'm now going to have not an AB, but an XB. and not an XY, I'm going to have an AY, which is exactly what's happening in this case. So if I write this out again, right, so lead nitrate plus potassium iodide goes to, right, and if I circle my cations here, one cation is lead, one cation is potassium, I'm switching them so that I now have potassium nitrate, or sorry, let me do this so that it looks more like the one up. No, that's right. Yeah, potassium nitrate and lead iodide. Now you'll notice, if you're, for those of you who are following along or are a little more savvy, you may notice, right, that I had two nitrates here and now I don't have a nitrate, or I had only one iodine and now I have two iodines. What I did was I switched the cations, but I made sure that the compound still made sense. So I didn't put one potassium with two nitrates because that's not an overall neutral compound, right? We know potassium's +1, nitrate is -1, so there should just be a 1-to-1 ratio. Ditto, this lead must be +2 because each of the nitrates are -1. So lead must be +2, so when I combine it with iodide, it must be that there's two -1 iodides so that it's all neutral. So keep in mind that these things are going to be neutral, and you're going to need to balance like we did in this equation, right? Put a 2 in front of the Ki, 2 in front of the potassium iodide, or potassium nitrate, excuse me. But it's a type of double replacement reaction. And double replacement is just an observation of what's going on with the formula, but really the reaction type, the chemistry that's going on, makes it a precipitation reaction because something precipitated out. This yellow solid is sometimes called the precipitate, right? The yellow solid is called the precipitate. And that is a solid that forms during a reaction because of a reaction. Precipitate is a solid that forms because of a reaction. Right, so it's a solid that forms out of solution there. So again, right, I was saying that a precipitation reaction is just when you start off with two aqueous things. So that means, well, neither of these, those are both gas for the first one. Here I have aqueous, that's good. This third one I have solid and a gas, that's definitely not a precipitation reaction. And for the last one I have aqueous and aqueous, that's good. But remember that I had to start off with two aqueous things and I end up with a solid. So if I look at my third example, I have aqueous sodium nitrate, but I have a solid silver chloride here, so that's good. And if I look at the last one right here, I have a liquid water and I have aqueous potassium bromide. So I know that that is not a precipitation reaction. This is not a precipitation reaction. This is a precipitation reaction. Again, because I started with two aqueous things and I have one product that is a solid. That's going to be true for all precipitation reactions. So how do I know? In this case, I was given all the states, aqueous, solid. I was given that, but even if I'm not given that, I should have some idea of what's likely to be water soluble and what's not likely to be water soluble. And we're going to have just kind of like a general, at this point, a general idea of being able to predict whether things are water soluble or not. So let's take a look at this reaction and kind of draw some abstract diagrams of what's going on here so you can kind of picture it a little bit better. If I have two, I'm going to draw these two different solutions here. So I've got a lead nitrate solution. So I'm going to have one big thing here of the lead nitrate solution. So these are aqueous, right? So we know there's water everywhere. And since it's aqueous, what that means here is that the lead 2+, is floating around by itself. The nitrates are floating around by themselves. And all of these ions are floating around in solution. They're just kind of randomly going everywhere, kind of like we'd think of it like a gas, but they're not a gas, right? They're just randomly floating around, diffusing throughout the whole solution. Now I also have the potassium iodide. Same situation, bunch of water molecules. I'm only going to draw 3 and not 17 million trillion. But it's the same idea for the potassium iodide, right? We got K pluses, we got I minuses, we got K pluses. We've got all these ions that have dissociated. They're no longer stuck together. They are surrounded by water molecules and they're in a solvation sphere, which we can talk more about later. But They're separate and they're floating around. The idea here, if I draw this last picture for when you mix the two, right now you mix the two, and now you have water molecules. Again, lots of water molecules all over the place. And initially here, what you see is that initially you might have like a lead 2 plus over here and a nitrate over here. Sorry, that should be a NO3. I just saw that. And you might have initially a K plus and maybe like an I minus. But the issue is, as soon as lead starts to hit or bump into the iodides, the idea is that it sticks together and it forms this solid. It sticks together more than it wants to be by the waters. And so then you start to form, right at the bottom, all of these lead iodide particles. They form solid and they don't dissolve in the water anymore. And which is why we see that yellow stuff form. In this case, it's yellow. It doesn't have to be yellow. But in this case, lead iodide is yellow. They stick together and then they crash out. They quote unquote crash out or they precipitate out, which is why that yellow forms. So the idea here, right, again, is that in these separate aqueous solutions, these ions are all separate. They're just surrounded by water. They're clear. They're colorless. Same thing for the Ki, the potassium iodide. These ions are all separated out. They're surrounded by water molecules. But as soon as they come together, every time a lead finds an iodide, it's going to stick to it. It's not going to let it go, and it forms a solid and sinks to the bottom of the reaction vessel of your flask. And that's what a precipitation reaction is. You've mixed two things, and they join up and they form solids. Now, these lead iodides are not soluble anymore. And by not soluble, we mean very, very, very poorly soluble. So how do I look at a reaction and decide what things are soluble and not soluble? We're going to follow these basic solubility rules here. Our book has this table 4.5, for just trying to find what combinations might be soluble or not. So if you were to read this matrix, something like calcium hydroxide would be soluble, but calcium carbonate, CO3 down here, would be slightly, they say slightly soluble. What they mean by slightly soluble is not soluble. They mean less than a gram per liter dissolves. That's kind of like what chemists use as the defining, let me write that down for you. Basically, anything less than being able to dissolve 1 gram per liter is considered insoluble. Here they're calling it slightly soluble because everything dissolves a little bit. Almost everything dissolves a little bit. But if it's less than a gram per liter, we generally call it insoluble. So like we'd consider oxygen, O2, to be insoluble because you can't get very much of it in water. Same thing with like oils and fats. You can't get much of it in water. So we call it insoluble. Technically, you can get a little bit in. Thankfully for all aquatic life, right, you can get a little bit of oxygen dissolved in water. Otherwise, fish wouldn't live. But chemists would call that insoluble. It's just so little we don't even count it. But I don't care that you like memorize these matrices or anything like that, or these big long lists of rules. The ones that I want you to mostly focus on for my class is these 3 simple ones right here. As far as cations go, if you have an alkali metal, so those group 1 things, sodium, potassium, lithium, etc., or an ammonium cation, if those are in the compound, they're water soluble. Those things are going to be water soluble. So sodium chloride is soluble, ammonium chloride is soluble, potassium fluoride is soluble. Anything that has an alkali metal or an ammonium in it is going to be water soluble. As far as anions go, the second half thing, right? Any salt that has nitrate or acetate, we're going to say is soluble. So if it contains like carbonate or sulfate or something like that, maybe, maybe not. But acetate and nitrate definitely are. And then the little third rule here is just we've got kind of these naughty metals here. We've got mercury, lead, and silver. They tend to not be water soluble, like for most all their compounds. The only time lead, mercury, and silver salts are reliably soluble is if they're combined with the anions up above. So if you have like lead nitrate or lead acetate, that is soluble. Or silver nitrate or silver acetate, that is soluble. But if you have silver sulfide, if you have silver oxide, those are probably not very water soluble, is the idea. So if let's use these examples up here. So if I look at this lead nitrate here, I've got lead nitrate. I see that nitrate is one of these, and anything that has nitrate in it is going to be soluble. So I can say that the lead nitrate is soluble. Even though it has lead in it, it's combined with nitrate, which means it is soluble. Now, if I look at my potassium iodide, I see that, well, I've got potassium, that's an alkali metal, so I know that that's soluble because it has an alkali metal in it. I don't care that the other thing is iodide, the other thing could be anything. It's that it has an alkali metal in it, so it's going to be soluble. If I look at my potassium nitrate, second thing, this is a twofer. I know that both alkali metal and nitrate make things soluble, so that's definitely soluble. And then if I look at lead iodide, I see that I've got lead, which is one of these naughty metals, and iodide, but iodide doesn't help me out at all. So it has lead in it, so I think that it's not water soluble. So I'm going to say it's insoluble. Insoluble, which is why we write a solid mark, right? It's not dissolved in water. It's not aqueous. It's solid. It's just a separate phase, right? You can filter this stuff out now. You can keep that yellow powder behind a filter paper, and then all of the clear liquid, the rest of the solution will go through it. So we're going to practice this in just a sec. So I left these solubility rules up here. I might do the first 4 for you, and then I want you to pause and try to do the other 4, or you can pause now and try all 8. I just want you to circle the compounds that are likely water soluble. So if I'm looking at sodium chloride, what I see here, I see sodium, which is one of the alkali metals, so I'd say yes, it's water soluble because it's an alkali metal. I look at the second thing, I see a potassium, also an alkali metal, circle it. I see the third thing, I see lead, which I know is one of those naughty ones. Here's the lead, it's not soluble, so I don't think that's soluble. It's with chlorine. Right here I have lead chloride. I don't have lead nitrate or lead acetate, so I don't think that's water soluble. But in the next one, I have lead acetate. I do have acetate in this one, so now I do have lead acetate. Oh, whoops, I'm sorry, that's not acetate. Did I? Whoops. This is lead acetate. Does not have this. Oop, sorry, lead acetate should be PbCH3. CO2 2. Regardless, I have lead, I have acetate. Oh, that's why it's up here. Sorry. Let's see, what can I do? Let's see if I can do this. No, can't. Sorry, acetate, that's the wrong formula for acetate. That's my bad. I accidentally got another 2 hydrogens in there. Acetate is this, right? CH3CO2 minus. And I think I copied and pasted that in a bunch of places, so I'll try to fix that. Acetate. And you should know that, right, from the naming ionic compound stuff. Regardless, lead is normally not soluble, but it's with acetate, so now I'm going to say it is soluble. Lead acetate should be soluble. So you should pause, take a look at these last 4, and see if you can decide which ones are soluble in water and which ones are not soluble in water. Okay. Wet my whistle. So same deal. I look down here. I see that I've got mercury, which is one of those metals that doesn't tend to dissolve in stuff. And it's with carbonate, which is not nitrate or acetate, so I don't think that's going to be soluble. Here I have the silver, again one of those naughty metals, but it is with nitrate, so I think that's soluble. Here I have ammonium, so I think that's soluble. And here I have silver again, but not with nitrate or acetate. It's only with chloride, so I don't think that's soluble. So that's how we'd apply these solubility rules to some of these compounds. Again, I don't expect you to like memorize the solubility of everything. If I ever give you any examples that go off that diverge from these 3 rules up here, I will give you solubility tables, and I will tell you very explicitly whether or not it's soluble. There's no reason why you have to just memorize a bunch of trivia about things that are soluble and things that are not. So for practice for you, right, I just want you to add the phases to each of these species. I'll draw them below. I should have left more space here, but draw the phases, and by phases I mean right? Are these things solid, liquid, gas, or aqueous? Are they solid, liquid, gas, or aqueous? So mostly I just want to know, and let me just write this a little bit better for you all. I know in my mind I think a lot faster than I'm right, than I write, like I'm sure most all of you do. And so I just don't have the patience to take my time to write. Hopefully that looks a little bit better. Solid, liquid, gas, or aqueous. So mostly I just want to know, basically, are these solid or are these aqueous? They're all going to be in solution here. So why don't you pause, see if you can do that, right? We're just going to follow the solubility rules, right? If it's soluble, we're going to say aqueous. If it's insoluble, we're going to call it a solid. And then at the end here, I just want to know, so therefore, which one of these two is a precipitation reaction? So why don't you pause, take a crack at these. Okay, so if I'm just going to go through these real quick here. Lithium bromide definitely should be aqueous because it's got lithium in it. I've got silver acetate, also aqueous. Lithium acetate, definitely aqueous, right? It's definitely soluble. And then silver bromide, solid. That is not soluble, right? That's silver with bromide, which is not going to help it be soluble. So I have three soluble things: soluble, 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 insoluble. And maybe I should write that note here for you all just to kind of doubly emphasize it. Solid means that it's insoluble in water. For these precipitation reactions, insoluble in water, in the context of precipitation reactions, solid means that it's insoluble in water. And then aqueous always means that it's soluble in water. And then for the second reaction, right, same deal. I've got acetate here, so I know that that's going to be aqueous. I've got a sodium here, so I know that that's going to be aqueous. I've got sodium and acetate, that's aqueous. And then I have water, which is straight up water, so I'm just going to say that's a liquid. I mean, I know water is a liquid. The only reason you don't say aqueous for water solutions is that you're not saying that water is dissolved in water. That's what aqueous means. Aqueous means dissolved in water. So it doesn't make sense to say that water is dissolved in water. Water is just a part of the bulk, pure substance, the water. So you just leave it as liquid. Now, if I go back down here, right, it's saying, well, which of these is a precipitation reaction? We all know now that I have to start with two aqueous things, check and check, both of those work. And I need to end with the solid, and only this one ends with the solid, right? The silver bromide should be a solid, and the second one, water is a liquid, that's not a precipitation reaction. So hopefully at the end of this video, you have a little better sense of the solubility rules, just some basic solubility rules for ionic compounds, and what a precipitation reaction is. Now we're going to compare and contrast this to combustion reactions, acid-base reactions, and redox reactions, but this should get you going. So study up and good luck.